Okay, perhaps we can start. Welcome everyone to the last talk of the day. This talk will be presented by Professor Thierry Lahaye from Laboratoire Charles Fabry, CNRS and Institut d'Optique. The talk will be on quantum simulation of spin models in arrays of Rydberg atoms. Before Dr. Thierry starts his talk, I will say a few words about him. So he is an experimental physicist working in the field of quantum engineering using arrays of cold atoms. He is in CNRS and, as I said, working in the quantum optics group of Institut d'Optics. So he's also a co-founder and scientific advisor of the startup Pascal. I think he will say a few words about this startup at one point. And among his many accolades and awards, one is Louis Armand Prize for the French Academy of Sciences for the first realization of the purely dipolar quantum gas. So let me hand over the stage to Professor Thierry Lahaye for this interesting topic.
Okay, thank you. So thanks for the kind words, and thanks for the opportunity to present our work in this very nice webinar. And so I was tuning in yesterday and this morning, and we had already interesting introductions and about using those arrays of single atoms in optical tweezers and using Rydberg interactions for either quantum computing or for some kind of computational problems like graph combinatorics and stuff like that. And I will focus on quantum simulation of spin models using this very same platform. So this work is done at the Institut d'Optique in the group led by Antoine Brouet, and here are the people over the last few years that contributed to these experiments in the lab. And also we have strong collaborations with Hans-Peter Büchler in Stuttgart and Andreas Leuschli in Innsbruck on the theory side. And this was of course very important for us to interact with those theoreticians. All right, so in a nutshell, we use arrays of single Rydberg atoms. We can place them in pretty much arbitrary geometries in 1 and 2D, and we can have up to 200 atoms. So these are examples of such geometries that we can do. And the spacing between those atoms is a few micrometers, which makes it very easy to optically detect them and manipulate them. However, of course, if you keep them in a ground state, they just don't interact at such large distances. And so to have interesting physics going on, we excite them to Rydberg levels, such that we have strong interactions, typically in the megahertz range for distances. And this means that the dynamics occurs on microsecond timescales, to be compared with the lifetime of those Rydberg levels, which is pretty long, hundreds of microseconds. And so to a good approximation, you have a closed quantum system undergoing a unitary evolution. And what's maybe even more important is that those arrays of Rydberg atoms, they implement in a very natural way without having to do any fancy engineering. They implement spin models that you encounter in quantum magnetism. Namely, if you use van der Waals interaction between these atoms, you will implement the Ising model. And if you use two different Rydberg states interacting via the resonant dipole-dipole interaction, then you implement this type of spin model where you have flip-flop type of interactions, and this is called the XY model in quantum magnetism. So this is the outline of my talk. I will first take a bit of time to tell you about our experimental setup, and in particular about recent developments in our group. And then I will give examples of simulations, both of the Ising model and then of the XY and XXZ models. All right, so let's start with the experiment. I will be brief on this part because you've heard already quite a few talks about this. So We use single atoms trapped in optical tweezers. So this is a sketch of our experiment. We have a vacuum chamber inside which we have high numerical aperture aspheric lenses. And we can use them to focus a dipole trap at 850 nanometers to a spot size, which is about 1 micron. And then around this trap, we have a motte of rubidium atoms. And in fact, you can collect cold atoms in the optical tweezer. But because of the very small size of this dipole trap, in fact, the light-assisted collisions, if you have several atoms in the tweezer, are extremely efficient and extremely fast. And so you will lose the 2 atoms as soon as you have 2 atoms in the trap. And so this means that essentially in such a tiny optical tweezers, you have either 0 atom or 1 atom, but never more than 1. And so you have a 50% probability, roughly, to have a single atom in your optical tweezer. And this is something that you can observe by collecting the fluorescence emitted by at 780 nanometers by the atom on a camera, for instance, and you see this kind of telegraphic-like signal with a low fluorescence level corresponding to no atom and a large fluorescence level corresponding to a single atom. So this was pioneered actually at Institut d'Optique 20 years ago in the group of Philippe Granger. And of course, if you want to do many-body physics, the first thing you need to do is to have many such traps. And so to do that, we use a spatial light modulator, which imprints a phase on the trapping laser. And in the focal plane of the lenses, provided you have calculated the appropriate phase here, you will get, for instance, this kind of square array of traps or triangular or honeycomb, kagome, or whatever. And then if you load single atoms into those tweezers, you can have these fluorescence images of single atoms in the arrays. And so this looks very nice if you want to do some quantum simulation. However, these are average fluorescence images taken over a very long time, such that you average the fact that you have either 0 or 1 atom in your tweezer. But if I take just a single shot image, for example, in this 10 by 10 square array here, what I will get is rather something like this, because only half of the traps will be loaded. And of course, this will vary from shot to shot, which means that this is a highly disordered system, and I cannot really do a clean quantum simulation with that. So this was the state of the art basically 5 years ago. And in 2016, what we did, and also at the same time in other groups, in particular at Harvard and in the group of Jae-wook Ahn in Korea, we went for assembly, atom by atom assembly of ordered arrays by starting from a larger array of 2n traps, which is loaded with n atoms, but in a random way. And then the idea is to move the atoms one by one using moving optical tweezers controlled by an acousto-optic deflector, such that in a few tens of milliseconds, you sort out all the atoms and get always the same desired pattern. And so at the time, we were limited to about 50 atoms, but with high filling fractions and a high repetition rate compared to other types of cold atom experiments. And since then, we have extended this first towards 3D arrays. And also now we have improved the number of atoms that we can trap in those arrays to more than 200 atoms. And these are examples of 1D and 2D arrays of about 200 atoms. And also one thing we have added is the fact that we can prepare geometries which are not just a subarray of a regular array, but really the geometry is arbitrary. And this is an example here where you have a square lattice with an edge dislocation here in the middle. And this is, of course, something which is quite appealing to be able to do that if you want to simulate condensed matter physics. And when you have such a thing in the lab, of course, you want to play a bit. So this is a rendering of Mona Lisa with single atoms. So it's not as famous as our little Eiffel Tower yet, but maybe it will catch up. All right. So one thing we've done over the last years is also to pave the way to increase the atom number even further by improving the vacuum. And this is something which is needed because, of course, when you want to assemble very large arrays, the time it takes to do this assembly increases essentially linearly with the number of traps that you want to have in your array. And at the same time, the lifetime of a configuration, due to the collisions with background gas, decreases with the atom number, because it's the single atom lifetime divided by the number of atoms. And so in our room temperature setup, what we have is a 20-second single atom lifetime. The vacuum is good, but not extremely good. And you see that this poses a limit which is about 200 atoms. If you want to assemble a bigger array, actually it takes too much time, and you will have some losses due to background gas collisions. And so if you want to really improve the number of, increase the number of atoms by large quantity, then you definitely need to improve the vacuum a lot. And so to do that, what we have recently demonstrated is that you can go to 6,000 seconds of single atom lifetime by going into a cryogenic environment. I would say a few words about this. And then the limit now is more like around 3,000 atoms. So this is something that is much bigger. So we have built this cryogenic setup, which is very similar to our room temperature setup up to this science chamber here, but we have appended a big cryostat here with a pulse tube refrigerator. And in fact, here the atoms are trapped inside the cryostat at 4K. And so this gives an extremely good vacuum. So this is a little bit how it looks inside. So this is where the atoms are trapped, and you see a system of nested shields that are cooled respectively to 30K and 4K by a pulse tube refrigerator. And here we have our lenses at 4K, and this is where we trap the atoms. And by doing that, we could measure this very long lifetime of 6,000 seconds. So this is actually quite challenging for the student to measure such long lifetimes, because you really have to repeat the experiment with long duty cycles. But you measure really a very large increase in terms of lifetime, and this is promising to go towards several thousands of atoms in principle. But of course, now the vacuum is not a problem anymore, but you have of course other technical issues to sort out, such as laser power to create lots and lots of traps, and also the field of view of the aspheric lenses is limited, and so on. So there are still issues that we need to work on to really reach those very large numbers, but it's promising. All right. So now we have our arrays of ground state atoms with tunable geometries, long lifetimes, and so on. And so the next thing, of course, is to have them interact by using Rydberg atoms. So I will not go into the details, because you've heard already a lot about Rydberg atoms. They have very large electric dipole moments, long lifetimes. And in practice, in the lab, we go to those Rydberg states by a 2-photon transition. And we can have a nice coherent oscillation here, as you can see, with Rabi frequencies, which are typically in the megahertz range. For some experiments, you will see that actually we use 2 different Rydberg levels, NS and NP. So depending on N, they will be separated by a transition frequency from 10 to 20 gigahertz or so. And by applying microwaves, we can also drive nice coherent Rabi oscillations between those 2 states, as you can see on this graph here. So the very reason why we are using Rydberg states, as I said, is because they strongly interact. So if you take 2 Rydberg atoms separated by a distance r, they mainly interact via the dipole-dipole interaction written here. And so depending on how you prepare your 2 atoms, this dipole-dipole interaction will lead to different physics. So if, for instance, you prepare 2 atoms in the same Rydberg level, in fact, to first order, this dipole-dipole interaction has no effect, and it shows up only in second order in perturbation theory, and it leads to a shift of this doubly excited state here by a quantity delta E, which is given by a 1/r⁶ interaction, and this is called the van der Waals interaction. And now you you can select two states in your atom, the ground state and the Rydberg level. And if you map a spin 1/2 onto those two atomic states, in fact, you will see that you get an Ising type of interaction. There is another interesting regime where you prepare one atom in a Rydberg level, like NS state, and the other Rydberg atom in a P state, for instance, a P Rydberg state. And then if you do that, for instance, prepare the state SP, this is degenerate in energy with the state PS, and those two states are directly coupled via the dipole-dipole interaction. And so now, if you encode your spin 1/2, spin up, spin down in those two Rydberg levels, so it's a different encoding, then in fact, the dipole-dipole interaction acts as a flip-flop. And so this is an XY spin model, where the prefactor here, the interaction, decays slowly as 1/r⁴ with the distance between the atoms. And so in our experiments, we use both types of interaction depending on what we want to do. And I will first describe simulations of the Ising model. Unless there are some questions on this experimental setup, maybe I would be happy to answer any question if there are.
So far, there are no questions. Maybe
right.
Umakant has
yeah,
a question. He raised his hand. Umakant, you can please go ahead and ask them.
Yeah, a quick question on this XY model.
Yes.
Is it possible to kind of apply some static magnetic field and reorient the dipoles or something?
Yeah, so you would most likely do it with electric fields because these are electric dipole moments.
Yeah, in this case.
And
yes.
yeah, and this is certainly something you can do. However, you will see that in fact, in the end, this XY model, by applying some microwaves, you can mimic the effect of an external B field for spin models. And so, but in principle, yes, you can use also electric fields and magnetic fields to tune a bit the structures. And these are things that we do from time to time. I will say a few words about this later.
Yeah, sure. Thanks.
All right. So maybe if there are no other questions, I can maybe move on, or maybe there is one.
There is one question in the chat box.
Yeah.
What is the advantage of having optical lenses inside the vacuum chamber?
Yeah, so this is a very good question. So in fact, the advantage is that the setup is relatively simple, and this is actually a technique that we pioneered 15 years ago in the group. It's and especially at the time, it was much simpler to use just an aspheric lens rather than a complicated microscope objective. However, of course, now there are many experiments where people do essentially the same physics with having microscope objectives outside of the vacuum chamber, and this is working just fine. In our case, we use these aspheric lenses because the system is quite simple. We can use a relatively big vacuum chamber such that inside the vacuum chamber we have electrodes for applying static electric fields to cancel, for example, stray fields and so on. So I would say that yes, there are advantages but also some drawbacks. In the case of the cryogenic setup, of course, having the lenses, you need to have the lenses pretty close to the atoms. So this means they need to be at 4K. And so having a microscope objective at 4K is more challenging because when you cool down, you have a strong mechanical stress and so on, and your objective may not work as nicely. So, but I would say it's obviously not something which is better for all aspects with respect to microscope objectives. It has some pros and some cons. Disadvantage of those aspheric lenses is that, of course, off axis they do have some aberrations, much bigger than what you have in a microscope objective, where you can do the optical design in such a way that you do not changed. You do not have too much coma, for instance, off axis. So if you want to do big arrays, in fact, this is one of the limitations of those aspheric lenses inside vacuum chambers. All right, so maybe I switch gears and describe the first type of quantum simulation using the Ising model. Let me very briefly remind the concept of Rydberg blockade. And you've heard about this, for example, in Mark's talk or in Jehud's talk this morning. Again, if we have our two-level atom with ground and Rydberg state, and we drive on resonance Rabi oscillations, we'll have this nice Rabi oscillation I was mentioning before. And now if you have two atoms and you start from the ground state, if the two atoms are closer than a blockade radius, then the second step of excitation is forbidden. And in fact, you prepare this entangled state here. And this is the basis for two qubit gates, for instance. And also it allows you in principle to do multi-qubit gates. But what we are interested in is a regime where we have blockade, Rydberg blockade in the system, but not over the entire system, but rather just between nearest neighbors. So essentially, you have a Rydberg blockade, which is comparable to the lattice spacing in your array. And then you will observe some strongly correlated many-body dynamics. And in particular, recently, we have used this system to do a quantum simulation of 2D antiferromagnetism with about 200 atoms. And this was done in collaboration with Andreas Leuschli in Innsbruck on the theory side. And this was published last year, back to back with the Harvard group, where they studied very similar physics. And so we have our array of atoms, and again, each atom has this spin down and spin up level, and we can apply this laser with a Rabi frequency omega and the detuning delta. And so if you write the Hamiltonian of the whole system, you've got a single particle part of the Hamiltonian, which corresponds to the laser driving with a Rabi frequency and a detuning. And you've got the van der Waals interactions between atoms I and J, decaying as 1 over R to the 6th, and they appear only if both atoms I and J are in the Rydberg level. That's why you have this projector here, RR, which counts the Rydberg atoms. But now if you rewrite this in terms of Pauli spin matrices, in fact, this Ni and J term involves some sigma Z terms. And so this means that you have essentially Ising couplings in your system. And so we want to investigate what happens when you want to prepare the ground state of this system in a regime where the blockade is just barely above the lattice spacing. And so if you want to accommodate as many Rydberg atoms as possible, fulfilling this Rydberg blockade in the system, what you expect is to get this kind of checkerboard pattern. And this is an antiferromagnetic ground state if you speak in quantum magnetism language. And of course, for a finite system like this with an even number of atoms on each side, you have actually two such ground states. So experimentally, the way we want to explore that is by some kind of adiabatic preparation. That is, so this is a sketch of the phase diagram of the system, and we can prepare easily the atoms in this paramagnetic phase here, all the atoms in spin down, and then we will ramp up the Rabi frequency of the system, then sweep the frequency of the lasers, and then ramp down the Rabi frequency of the lasers. And so if we do this properly, we should end up in this antiferromagnetic dome here. And you need to vary slowly enough those parameters to try and stay adiabatic. So if we do this in the experiment on a small 6x6 square array, for instance, at the end of the experiment, we measure which atom is in which state, either Rydberg or ground. And we can do a histogram of all the outcomes of the experiment when we repeat it many times. And you see that out of the 2 to the 36 possible states that can appear in the system, in fact, there are 2 states that appear very prominently with a probability close to 10%. And these are precisely those antiferromagnetic states. And in fact, here, most of the states that we have here, they correspond to this state where you have one bit flip. And this corresponds actually, it's not a problem in the preparation of the system, it's more a readout error that sometimes from one atom we will infer that it was in the Rydberg state, whereas actually it was in the ground state. And so this, of course, it's a bit flip error during the readout. And this explains most of this kind of grass that you have here, this noise. And we can actually do it even on larger arrays, and even on a 10 by 10 array, from time to time, when you have no errors, you get this perfect antiferromagnetic ordering. So this is really a picture taken by our camera at the end of the sequence. Here you see every second atom, because those atoms that are missing, actually, they were excited to Rydberg levels, and so they were not observed by fluorescence at the end of the sequence. All right, so then, of course, you need to do some quantitative physics. So the thing you want to plot is a correlation function. And so this is the experimental correlation function that we measure. So you see this kind of nice alternation of signs when you plot this spin-spin correlation function. And here at the bottom, it's actually for the same experimental parameters, what is predicted by our theory colleagues without any adjustable parameter when they do matrix product states simulations, and you see that the agreement is actually really pretty good. And experimentally, we can actually push the system size, for example, to 14 by 14, and observe still these very nice antiferromagnetic correlations. And of course, for such sizes, our theory colleagues just can't do at all those simulation of the dynamics of the system, because it's just totally out of the question, even with an MPS ansatz. All right. So then we can compare quantitatively what happens on your system, for example, by plotting the staggered magnetization during the ramp here. And you see that for small sizes, we have really a good agreement between experiment and theory. When we go to larger arrays, in fact, we see that a perfect ideal Hamiltonian without any experimental imperfection would give us the yellow curve here that you see here. And in fact, to get back to the experimental results, we need to take into account some experimental imperfections that we measure independently. One of them being, for instance, the fact that our atoms, they are not pinned exactly at the bottom of the tweezers, but they fluctuate very slightly from shot to shot due to their finite temperature. And this yields some, in fact, this disorder in position of the atoms gives some disorder in the interaction strength for spin Hamiltonian. And this is on a 10 by 10 array, for example, this is enough to significantly decrease the evolution of this staggered magnetization. So this is in some sense a very nice test bench for us to know on which kind of experimental imperfection we have to put our efforts in the future. All right, so of course, when you talk about antiferromagnetism, the next thing you want to try is a triangular lattice. And in those experiments, it's quite easy to change the geometry. And so if you have just even a triangle like this, and you say, okay, let's put some Rydberg atoms here and the ground state atom here, on the third one, you don't know what to do, because basically you cannot fulfill all the antiferromagnetic constraints at the same time. And so on a large array, even at the classical level, you have a macroscopic degeneracy of the classical ground state. And so in these frustrated triangular lattices, it's kind of interesting to study this onset of interaction of antiferromagnetism. And so, in fact, the phase diagram for the triangular lattice looks a little bit like this. So you've got this paramagnetic phase, and then you've got a dome here where you have two subdomes at 1/3 feeding and 2/3 feeding, where you have a nicely organized pattern. For example, at 1/3 feeding, you have every third atom in a nice triangular pattern, which is excited to the Rydberg state. So there is no frustration here. The same here for this 2/3 pattern, you just reverse spin up and spin down. And in fact, the most interesting effect of frustration lies here in between those two lobes, because quantum mechanical fluctuations lead to what is called order by disorder phases, where you have a macroscopic degeneracy in the of many ground states in the absence of a Rabi frequency. So here you have the classically frustrated state, but applying a transverse field, this h bar omega here, actually selects some of those states, and you should see some subtle order here appearing. So we have started to explore this phase diagram, and in particular, in this 1/3 phase, we can plot those histograms. So I have no time to go too much into the detail, but we plot at each realization of the experiment the number of atoms that lie on each sublattice A, B, or C from this triangular lattice. And we observe clearly a kind of triangular shape with vertices here around NA, NB, and NC, which corresponds to the perfectly ordered states. And you see that the experimental results on the top are really comparable to the simulation results that you expect here. And we can measure again correlation functions and so on. You can also explore this 2/3 phase here, where in fact you still have a triangular shape, but it's actually flipped with respect to the previous case. And of course, the next step will be to investigate in detail this order by disorder phase, and to have a hope to observe this phase. Actually, we know that we need to work on this positional disorder I was mentioning briefly before. All right. So in the final part of my talk, I will move away from the blockade physics and from the van der Waals interactions that give rise to this Ising model. And I will actually focus on the so-called XY model, where we use the resonant dipole-dipole interaction between those Rydberg states. So you remember this slide. The idea is to, for instance, to encode the spin up and spin down in the Rydberg manifold with an NS and an NP state. And so you have this flip-flop interaction. So to do that, so as I was saying, we encode the things in the following way. And so to couple those two states, we use microwaves, as I said, between 10 and 20 gigahertz. What's nice about Rydberg atoms is that they have these very large dipole moments. So this means that actually you don't need a lot of you don't need a lot of microwave power to get large Rabi frequencies. For those of you who are used to driving microwave transitions between hyperfine states of the ground state of rubidium or cesium or whatever, in general, the experimental problem is that you never have a big enough amplifier. In our case, we don't need amplifiers, and actually, in general, you even need microwave attenuators because you have too much power. So, of course, with microwaves, one thing which is not so nice is that on the scale of your array, which is a few tens of microns, the coupling is completely homogeneous because the wavelength here is a few, it's a few centimeters. And so, but we can still do some local addressing by light shifting one of the states, for example, the S state, the S state, by non-resonant optical addressing, either at 1005 or 1030 nanometers. And then, so this means that the Hamiltonian of interest that we have is this resonant dipole-dipole interaction with sigma plus sigma minus terms. So if we just take two atoms, these are experiments we did now quite a long time ago, but if you take just those two atoms like this at a given distance and prepare the state up-down, and then you just let the system evolve for a few microseconds, as a function of time, you will see what is the probability to get still up-down or the opposite state down-up. And if you do that, you observe these nice sine waves here, which are out of phase, which means that the system oscillates coherently between being up, down, or down, up. And you observe those coherent flip-flops over very large distances of even tens of micrometers. And you can actually then, in our setup, easily vary the distance between the atoms and measure this oscillation frequency here, which should be given by the dipole-dipole interaction. And when you do that, this is what you have here. It's a log-log plot, and the line here, it's not even a fit, it's an ab initio calculation that shows nicely the 1 over r to the cube that is a characteristic of the dipole-dipole interaction. Okay, so this dipole-dipole interaction, this XY spin model, it's actually quite interesting because it's so you can rewrite this Hamiltonian sigma plus sigma minus in terms of sigma x and sigma y matrices, and so this is whence the name XY. And another interesting way to see this this model is by doing a mapping onto a quantum particle that hops inside a lattice. And so this goes as follows. So imagine that I have, for instance, just 3 atoms like this. This one is a spin up and the 2 others are spin down. Via the dipole-dipole interaction, I can flip the 2 spins here, and I end up having down, up, down. And this state is also coupled, for example, to down, down, up. And so you see that when going from here to there, basically the spin excitation, the spin up, has moved from one atom to the next. And you can just, in a perfectly equivalent way, see this as a quantum particle which is hopping from side to side with a hopping matrix element J. But of course, and so it turns out that when you do this mapping onto particles that move around in a lattice, the commutation relations are those of bosons, but these are hardcore bosons because, of course, on a single lattice here, you cannot have more than one boson at the same time because, of course, an atom can have just one Rydberg excitation. And so this means that this is actually a nice system to study the physics that you have in general in the Bose-Hubbard model, except in the limit of very strong infinite on-site interactions. So actually, we have used this mapping, and I will not have time to go into the details, but 2 years ago, we have used, 3 years ago now, we have used this to study topological matter in the simplest setting, if you wish, which is called the Su-Schrieffer-Heeger model. So this is a one-dimensional chain where you have a particle hopping on a dimerized lattice, and you, depending on how your lattice geometry is arranged, you can have a trivial phase or a topological phase with edge states. And so this we could investigate. But contrary to many other experiments with cold atoms that were investigating the SSH model, in our case, we were able to also explore the regime where you have very strong interactions in the system. And there we could study a symmetry-protected topological phase, which had been predicted but never observed. And so we published this in 2019. And so this is a one-dimensional system, and in fact, topological matter is most interesting in 2D, where you can have some intrinsic topological ordering, and we are working towards this. And the first step that we took last year was to study the appearance of a spin-orbit coupling for our particle which hops from side to side. The idea is to still use the resonant dipole-dipole interaction, but now in each atom, we will not just use 2 levels, but 3 levels. So, but that's okay because Rydberg levels are a very rich internal structure. So, and that's an example of, as Umakant was suggesting, playing with electric fields and magnetic field. You can manipulate the positions of those states. And so, for instance, if you have just one S state, the state 0, and 2 P states, minus and plus. And if you have 2 atoms that you prepare in the state minus and 0, in fact, this excitation can de-excite this atom, exciting back to minus. And so this is exactly this flip-flop, this spin exchange that I was mentioning before. But in fact, there is another process which is allowed by the dipole-dipole interaction, is that this guy goes down, and this guy goes from 0 to the other state, plus here. And when you write down the amplitude for this process, you realize that actually the amplitude is a complex number. It has a strength W, but also a phase here. And so this is, in fact, in some sense, you can picture that as an excitation hopping from site I to site J, but changing in internal state, because you go from a minus to a plus, and also acquiring an orbital phase. And so basically this is exactly a spin-orbit coupling, because the orbital phase of the particle acquires a phase, and you change the internal state of the particle. And so in fact the minimalistic system where this gives rise to interesting physics is a triangle where so as you can see here, if you prepare a spin excitation minus on the blue atom, for example, and just let the system evolve, in fact, instead of spreading to other sites in a symmetric way, actually it will move in a chiral way. It will go preferentially towards the red atom and then towards the yellow one and back to the blue, and so on and so forth. And also due to the fact that you have hardcore interactions, now if you prepare two spin excitations, you do not have this chiral motion anymore, but you have a kind of symmetric motion of the particles. And so this is a very exciting ingredient for future studies with larger arrays, because there, in fact, you have a spin density-dependent density-dependent Peierls phase in your system. And again, this is something which in general is quite hard to engineer in cold atom systems. But here, due to this hardcore constraint, it's essentially built in the Hamiltonian. So you don't really have to engineer this thing. All right. So very briefly, in the remaining 3 or 4 minutes, I would like to tell you that we can also extend the type of spin interactions that we have in our systems. I told you we can do Ising, we can do XY, but of course there are other types of interactions like the Heisenberg model or its anisotropic version, the XXZ model. And in fact, it turns out that you can engineer this starting from the XY model using a type of Floquet engineering, applying a series of fast microwave pulses that allow you to rotate your spins very quickly. It's very reminiscent to what is done, has been done for decades in NMR in dynamical decoupling. And so we have investigated this in collaboration with colleagues in Heidelberg in the group of Matthias Weidemüller. And the idea is the following. So you have your atoms that are subjected to the XY model. And now you apply a pi/2 pulse of microwaves such that you rotate around the x-axis. In fact, then you exchange the role of the axis x, y, and z. And so in fact, your atoms will interact for a given time here, tau2, under the Hamiltonian hxz. And then you can apply another pulse such that you interact via hyz. And then you can rotate again the axis such that you come back to xy. And if you do this very fast and you repeat it many times, in fact, in the end, the average effect on your spin system is, in fact, given by let me skip this. It's given by this type of average Hamiltonian, where you have all three terms, sigma x, sigma y, and sigma z. And you see that the prefactors here are given by those timings here of the pulses. So just by programming your microwave pulse generator, you can actually change the weight of all those three spin-spin interactions. And this is something that that is interesting, because you can, for example, go from the XY to the Heisenberg model, or to something which is closer to the Ising model, but with a little bit of XY and so on. And so just to illustrate this, we did a small experiment with a small 32 atom array in this kind of diamond configuration. And the idea is that we initialize all the atoms along the Y direction. So if you really realize the Heisenberg model, in fact, you should expect that this is an eigenstate of the Hamiltonian, and so it should not evolve in time, and the magnetization of the system, for example, should remain constant. However, if you are in the XY case, then this thing is not an eigenstate, and the magnetization should relax pretty quickly, actually, towards zero. And so in the experiment, what we do is, during the first 3 microseconds, we apply our pulse sequences. So we have this Floquet driving, and we observe this kind of Heisenberg Hamiltonian, and the magnetization is almost constant. There is a little bit of decay, but very little. And as soon as we switch off the microwaves, you observe this strong decay of the magnetization. So this is just to illustrate that we can dynamically tune XXZ Hamiltonian, and this is something that we'll explore a lot in the future. All right. So in conclusion, I hope I have convinced you that those arrays of Rydberg atoms are also a kind of ideal platform for quantum simulation of spin models. You've heard already that they are also very nice for quantum computing. The fidelities of the gates and so on are steadily increasing over the time. And so, in fact, now there are even startup companies, among which one that we founded at Institut d'Optique, where the idea is really to build now commercial machines that do exactly this kind of quantum simulators and little specialized quantum computers. And Loïc Henriet from Pascal will describe this tomorrow in much more details, I guess. And with that, I'd like to thank you for your attention.
Thanks a lot, Thierry, for this fantastic talk. And also thanks for showing those nice images. Are there questions? Okay, there is already one question for Vinit Bharti. Just allow me to read. Do you have motional decoherence effect due to the thermal spread of positions of atoms inside the traps?
Yes, we do. This is clearly one of the effects that we observe. So in fact, I was mentioning this positional disorder that we have in our arrays, and this has essentially 2 contributions. The first one that we are working on both, actually. But so the first contribution is the fact that the atoms in the optical tweezers, of course, they are not at 0 temperature, and so from shot to shot, you will have a tiny change in the position of the atom on the 100 nanometer scale. So for a typical interatomic distance of between 5 and 10 micrometers, it's not a lot, but it's non-zero. And so this gives rise to observable effects. And for example, in those Ising simulations, we have seen comparing with simulations taking disorder into account or not, that this starts to have an effect. So that's the first thing. But even so, and the way to circumvent that is to do some Raman sideband cooling in the tweezer to really reach the ground state in the tweezer, the vibrational ground state. And this is something that we have implemented very recently in our setup. So this issue is not there anymore, or at least it's very strongly suppressed. The next, actually, there is another issue, is that when you say you square regular lattice, We are using these tweezers with a spatialized modulator and so on. And so, in fact, nothing guarantees that you have a perfectly periodic lattice. It's not like in an optical lattice where you, it's neglecting curvature and so on, but where you have a really perfect ruler between your traps. Here, we have a bit of fluctuations. It's hard to measure, but we have ideas how to do that, and then how to try and counteract that. Once you are able to measure these little deviations from perfect periodicity, you can alter slightly the phase of your SLM pattern to try and make this even more regular. And so these are things that we plan to work on in the future.
There is another technical question from Professor Ajay Vasan. How do you make sure of coherent exchange of spin excitation?
Well, so I'm not sure this would, so naively, the very first thing I would say is that the fact that you observe this nice sinusoidal oscillation of the probability to be in up down or down up is already a good sign that you have a coherent exchange, because but we've made other experiments where you can even manipulate the relative phase between the two parts of the wave function. So, for example, what we can do is prepare up down, then let the system evolve into an entangled state, and then apply a local light shift on one of the atoms to change the relative phase between the two parts of the wave function, and then see that you can suppress, for instance, the spin exchange and things like this. And so, yes, these are the type of experiments that show this coherence.
There is another question from Manavendra Singh. Is it possible to simulate a DM spin interaction, which is a vector spin interaction using Rydberg atoms?
So this is a very good question, an excellent one, I would say. And actually, this is something that we are. So the answer is yes. And the way to do that is to combine local addressing with a light shift and this Floquet type of engineering I was mentioning before. And so we are actually currently working on writing up a proposal paper, a theory paper, working this out. And this seems to be a quite appealing way of really doing exotic spin physics. So like the Jałodziński-Moria interaction, but even other types of spin models, which at first sight you say, okay, these are not physical, it will be very difficult to do in the lab, and actually it's possible within this Floquet engineering type of approach, which of course, it has some limitations because it works only in the limit of very fast pulses, and so these are things that one needs to work out, but it's certainly possible. Yes, that's a very good question.
So there is one non-technical question from Yash Rao. Can you tell us more about Pascal?
Okay, sure. So yes. So Pascal was founded almost 3 years ago now, in March 2019. So by Antoine Brouets and myself, and by former physicists that did their PhD at Institut d'Optique with Alain Aspect and Philippe Grangier 20 years ago now, 25 years ago, that had been working in the industry in the meantime. And they were really convinced, probably even more than I and Antoine were, that the time was ripe for trying to make industrial machines, industrial versions of those experiments for applications both in the academia and also in the industry for all the industrialists that want to get their hands on practical quantum machines, maybe not strictly speaking computers, but quantum machines, and trying to learn what you can do with those machines. And so this was started, as I said, 3 years ago, and now the company has really grown up a lot. There are like 60 or 70 employees. A lot of them are former cold atom PhD students or postdocs. And they have built this beautiful setup here. As you can guess, this is not our lab setup. It's an industrial machine, which is based on exactly the same ingredients, say, but of course it's much more seriously engineered. All the computer control and all the optics and the laser packages and the vacuum system and so on are done in a very different way, much more reliable, much more automated and so on. And so the idea is that such a machine is made to operate, for example, in a HPC center. Such that you could imagine that this would be essentially a kind of a quantum coprocessor, if you wish. So you could couple these to a high performance cluster, for example, and use the quantum machine for what it is good at. For instance, quantum sampling, things like this. Coupled with a high performance classical computer, and this seems very promising. So of course we are not the only company working along those lines. There are other ones in the US and in Germany and in many other places. But it's a very interesting project. I'm sure lots of interesting physics, both on the theory side, because Pascal it's a full stack thing. It's also involved in the software and in the application layers. So I think it's really actually totally unexpected from my point of view. 5 years ago, I would not have even imagined such a thing, but it's really bringing a lot of new ideas and new techniques in the field. So I think it's really a blessing.
Perhaps we have time for one more question. So there is one question in the chat box from Priya Batra. The question is, can we simulate models which have transitions like many-body localization?
Yeah, so this is obviously also something that we have considered, and this is basically on the to-do list, because this is of course a very nice system where you can control the disorder and the influence of interactions. So there are some proposals out there to study many-body localization in 2D in particular, which is something for which there are not too many experimental systems where you can do that. I mean, there were beautiful experiments with ultra cold atoms in lattices, of course, but then you can think of different other types of disorder and so on. So this is for sure on the to-do list. Yes.
Okay, if there are no more questions, we thank Thierry again for this wonderful talk, and
Thanks.
I can hand over the session to the organizers.
Yeah, so thank you very much, Thierry, for a wonderful talk, and very nicely delivered, and it was really understandable, I suppose, by everyone. So yeah, so we Professor Bhanudas. Hello.
Yeah, okay. So I would like to thank Thierry. I think, and I can just echo what Umakant said. It's a really great talk, and so we look forward to hearing more about your group's work in the future.
Thanks.
Yeah. So good evening and good night. So bye.
Bye, everyone.
Bye.